everyone, and welcome to the Learning Curve Academy. In this lesson on statistics, I will be illustrating how to use the normal probability distribution to solve problems. And here we are told that the life of a certain make of electric light bulb is known to be normally distributed. So very importantly, we are told that the data is normally distributed, which means that the data points for the lives of the light bulbs follow a symmetric shape around the center, with a mean life of 2,000 hours and a standard deviation of 120 hours. These are the population parameters. Mu, the population mean, which is 2,000 hours, and sigma, the population standard deviation, which is 120 hours. Here we are asked for this normally distributed population to estimate the probability that the life of such a light bulb will be, starting with A, greater than 2,150 hours. So the first thing we'll do is that we'll set up our probability statement. So here I'm going to write the probability that X, where X represents the variable for which we're calculating the probability, which is the life of a light bulb. Here we're calculating the probability that X is greater than 2,150 hours. Okay, so this is our probability statement reflecting what we are computing, the probability that the life of a light bulb will be greater than 2,150 hours. So X here just simply represents the variable for which we are calculating the probability, which is the life of a light bulb. So the probability that X is greater than 2,150 is our probability statement. Now we're going to carry out a process of standardization. When we standardize, we apply this formula, Z equal X minus mu. This is for the normal distribution. We standardize a normal distribution problem of this type using the formula Z equal X minus mu divided by sigma. And that's what we're going to do now. So I'm going to convert this probability that X is greater than or greater than 2,150 to become the probability that Z, keeping that greater than sign, Z is greater than, and then I write the formula X minus mu all over sigma. Okay, sigma being the standard deviation. Now, let's discuss what these parameters represent. X represents the value for which we are calculating the probability. Mu is the population mean, and sigma is the standard deviation of the population. So what we're doing now is that we're standardizing the data set because it is normally distributed to allow us to read from the standard normal table. So this becomes the probability that Z is greater than, so we change from X to Z when we're standardizing, and we keep whatever sign we're using in the problem, which in this case is a greater than sign, and X is the value for which we're calculating the probability, which is 2,150. So here I will have the probability that Z is greater than 2,150, take away mu. Mu is given to us in the question as 2,000. That's the population mean, mu. And this will be all over sigma, the standard deviation, which is 120 hours. So that's sigma equal 120, the standard deviation. And all we're going to do now is that we're going to simplify this. So to simplify this, we get the probability that Z is greater than, now 2,150 take away 2,000 is going to give us 150. And so we have Z greater than 150 divided by 120, which is going to be equal to the probability that Z is greater than. And so now we simplify by dividing 150 by 120, which is 1.25. So this is Z greater than 1.25. So at this stage, it is recommended that we draw the standard normal curve to show this information. So here I'm going to draw the standard normal curve right here. And That's my standard normal curve, a symmetrically shaped curve with 0 at the center. And then I will locate 1.25, which is going to be somewhere here to the right of 0, because the values to the right of 0 are positive, to the left of 0 would be negative. Then I go upwards from the value 1.25 and I shade the area to the right of 1.25, indicating the area for which we're calculating the probability on the standard normal curve. That's the area greater than 1.25, or in other words, to the right of the value 1.25, which is the standardized Z value. So to calculate this probability right here, the probability that Z is greater than a positive value, using the full probability Z table. I will do other lessons using the half table, but in this case I'm going to be using the full table. So what I'm going to do here is that I'm going to say this is equal to, now because the probability of the entire curve, this entire normal, standard normal curve, the total probability adds up to a value of 1. Right? The total probability of this entire standard normal curve adds up to a value of 1. Because I need the area to the right, and the standard normal table, full table, only gives you probabilities of the areas to the left of a value. So that's something very important to understand, that when you read from the standard normal table, which is this table, the probability readings that you get for the Z-scores represent the areas to the left of a particular Z-score, always to the left. So if I were to, for example, read 1.10 here, this 0.8643 would give me would represent the probability of the area to the left, or we could say less than 1.10. It's always, when you read from the standard normal table, it always gives you the probability of the area to the left of a Z value, or less than a Z value. This is very important to understand that. So in other words, when I read for the probability of 1.25 from the standard normal table, what it will give me is this area, this entire unshaded area to the left. But that's not what I need in this question. What I need in this question is the probability that Z is greater than 1.25. So what I really need is this area to the right of 1.25. But when you read from the standard normal table, that is this table, what it will automatically give you, always and every time, it will give you the area to the left, or the area less than a particular Z value. Because that's not what we need, and because we know that the total probability under the entire curve sums to a value of 1 always, then to find the probability that Z is greater than a positive value, anytime you have this kind of situation where after standardizing you end up with the probability that Z is greater than a positive value, the simple way to find that is to just take 1 minus whatever the reading is from the standard normal table for 1.25. 1 here representing the total probability. And so what we're going to do now is to go to the standard normal table to look for 1.25, so that we can derive the probability associated with 1.25, which really will give us the probability of the area to the left of 1.25. But that's not what we need here. What we need is the probability of the area to the right of 1.25. So let's go down to the standard normal table, and here in the standard normal table we'll go to the Z column, we'll scroll down to 1.2, and then we'll go across on the 0.05 here. So 0.05 and 1.2. Of course, when we add 1.2 to 0.05, it gives us 1.25. So the reading that we're looking for is really this reading here, 0.8944. So 1.25, right? So you have to match the corresponding row and Y values for what you're looking for, the Z value that you're looking for. So we're looking for 1.2. So we come down in the Z column, go to 1.2 and then across on the 5, on the 0.05. And that is the probability reading at the junction there, here, 0.8944, represents the probability of the area to the left of 1.25. So 0.8944 represents the probability of the area to the left of 1.25. But that's not what we need. We need the area to the right of 1.25, and that's why we have to subtract from 1, as explained earlier. So what we'll do here is to just take 1 minus 0.8944, which is going to give us 0.1056. We could convert that to a percentage, and if we convert that to a percentage by moving 2 decimal places to the right, or in other words multiplying by 100, we would get 10.56%. So what this answer is saying is that there's a 10.56% chance that the life of a light bulb in this data set will be greater than 2,150 hours. Right? So that's how we solve this kind of problem. Now let's look at B. In B, where we have another greater than scenario, but as you will see, it's going to work out slightly differently. Here we're interested in the probability that the life of a light bulb, which is represented by variable x, is greater than 1910 hours. So to compute this probability, we're going to say the probability that z, again, we're going to standardize using this formula, x minus mu over sigma. We keep the greater than sign. Then we write the formula, keep this greater than sign, change x to z, and then write the formula for standardization. Standardization is necessary to allow us to be able to read from the standard normal table, this being the standard normal table. So it's probability that z is greater than x minus mu over sigma. And we will recall that x is the value for which we're calculating the probability. So I'm going to substitute here. So this becomes the probability that z is greater than, it's the probability that z is greater than x, which is 1910. Take away mu. And mu is the population mean of 2000, so it's 1910 minus 2000, and we're dividing by the standard deviation sigma, which is 120. So we divide by 120 here, and then we're going to simplify. So this is the standardization process. Once you apply the formula here, z equals x minus mu all upon sigma, what you're doing is that you're standardizing. So this becomes the probability that z is greater than, and we're going to take 1910 minus 2000, and this is going to give us negative 90 divided by 120, which is the standard deviation. So this is going to be, when we simplify this further, we have negative 90 divided by 120, and so we're going to get the probability that z, notice I keep carrying forward the z and the greater than sign until we have finished the problem by reading from the table and doing the necessary simplification. So this is going to be the probability that z is greater than negative 0.75. Now there is a negative table, a negative normal distribution, standard normal distribution table that you could read from, but in many exam situations you're not given a negative table. So I'm going to show you how to deal with those more complex situations where you only have the positive side of the table to work with. Let us look at, we have now standardized and simplified, and so we ended up with a probability P of z greater than negative 0.75. So let's see how this looks on the standard normal curve, and it's always recommended that you draw the standard normal curve to give you a visual impression of what you are working with. Now the areas to the left of 0 will be negative, so Negative 0.75 would be about here. And we go up from negative 0.75, and we need the area greater than. Greater than is always going to be to the right, so we'll shade the area to the right of negative 0.75. So that's the area that we are interested in, the area to the right of negative 0.75. But because this is a symmetric curve, the area to the right of negative 0.75 is actually the same as, in terms of area, it is the same as the area to the left of positive 0.75. So that's a very important thing that we need to understand about the symmetric properties of the normal distribution curve, that the area to the right of a negative value is the same as the area to the left of the positive of that value. Yes, so what we see here, therefore, is that the area to the right of negative 0.75 is exactly the same in terms of density as the area to the left of positive 0.75. So in effect, this problem could therefore be expressed as, in other words, the probability that z is greater than negative 0.75 could simply be expressed as the probability that z is less than 0.75. It would be the same thing because of the symmetric properties of the curve. And so because we know that the standard normal table, any probability reading from the standard normal table always represents the area less than a value, or the area to the left of a value, a positive value, then what we're going to do here is that we're just going to go to the standard normal table and we're going to look for 0.75. So here we go on the z, go down to 0.7, and then across on the 0.05. And the matching value there, again, go down on the z to 0.7, and then across to the matching value of 0.05. And so what we're looking for here is this probability, where the two values 0.7 and 0.05, which represents 0.75 matches. And that reading is 0.7734. That's the probability we're looking for, 0.7734, and that's the answer, 0.7734. Or of course we could say that this is 77.34%. So the interpretation of this would be that there's a 77.34% chance that the life of a light bulb in this population will be greater than 1,910 hours. All right. And now we're going to look at a more complex situation where we're working with an interval. And so we're going to set out this problem with its probability statement, which is how you generally start these problems, because we're asked to find here the probability that the life of a light bulb is within the range of 1850 hours to 2090 hours. We're going to set this out as an interval of values. So here's how we write this. We just simply say the probability that x is greater than 1850 but less than 2090. So that is how we'll set this up. All right, the probability that x is greater than 1850 but less than 2090. It's really just another way of saying the probability that the light bulbs will last between 1850 and 2090 hours. And so to standardize here, we will say probability. We're going to change the x here to z. And then I'm just going to write the formula on both sides because there are two numbers here to standardize, the 1850 and the 2090. So I'm going to write here x minus mu divided by sigma. Yes, I'm going to write x minus mu divided by sigma right there. We're going to write the formula where both of the values are, and of course we're replacing x with z because we have to standardize the results to allow us to read from the normal table. So we have x minus mu divided by sigma here. Formula is written twice because there are two values to standardize. So this will be equal to the probability. In the first place here, the x value is 1850. So I'm going to have here 1850 minus mu we recall that the value of mu is 2000 divided by the standard deviation, which you will recall is 120. Keep the less than sign that is here, keep the z value, keep this less than sign that is there, and then we're going to substitute on the right hand side in relation to the 2090 as we previously did for the 1850. Now substituting in relation to 2090 here is going to give us the x value in this case is going to be 2090, because 2090 is what we are calculating the probability for on the right hand side of z, minus the population mean, which we know from earlier is 2000 given to us in the question, divided by the same standard deviation of 120. So that's how we set this up, and now we're going to simplify. So to simplify this, this becomes the probability, and we're going to subtract here now 1850. So we're going to take 1850 minus 2000, and of course that's going to give us negative 150. So what I will have here is negative 150 divided by 120 less than z, which is less than, and on the other side we're going to say now 2090 take away 2000, and 2090 take away 2000 is going to give us 90 divided by 120. So now we are almost at the point of full simplification of the problem. So here we have the probability. Let's simplify this. It becomes the probability. We're going to divide 150 here by 120, right? 150 divided by 120, which is negative 1.25. It's negative 150 divided by 120. So we get negative 1.25 less than, write back this less than sign here, write back the z, which we're using to standardize, and then we have 90 divided by 120. So 90 divided by 120, which is 0.75. So this kind of situation is often the most challenging type of normal distribution problems when our interval involves a negative number here, negative 1.25, and a positive number 0.75. So what this simplified version of the problem is saying is the probability that z is greater than negative 1.25 but less than 0.75. So we're going to draw our normal distribution table to get a visual impression of this. So of course the value in the center is going to be 0. The value to the right of 0 here from the simplified problem, to the left of 0 rather, is going to be negative 1.25. But to the right of 0 here is going to be 0.75 positive. And then I'm going to shade this entire area. So I'm going to go upwards from negative 1.25, and I'm going to go upwards from 0.75 positive. And what we're interested in is this area that falls between these two values. Because recall that what we're trying to find here from the simplified probability expression is the probability that z is greater than negative 1.25 but less than 0.75, and that is the area between negative 1.25 and 0.75. So in these types of scenarios, when you're working from the full table, as we are in this problem, we're working from the full table meaning that it goes up to a probability of 1, as opposed to a half table which goes up to a probability of 0.5, in which case the reading for the final answers and their treatment have some slight variations, but I will be addressing that. So how we deal with these types of situations is that we will basically take the reading for the positive value first. The positive value here is 0.75. So when we have a standardized problem where one of the values, and the values below the curve here are called the z values, we have a standardized situation where one of the z values is negative and one is positive. What we do is that we first look for the reading from the standard normal table for the positive value. In this case, that's 0.75. And again, how to do that? We go to z, go straight down to 0.7 and then across on the 0.05 because we're looking for 0.75, and the probability reading here is 0.7734. So 0.7734 is the probability reading for 0.75. So what we did here again was to take the probability reading from the standard normal table for the positive value in the interval first, minus 1, which is the total probability, take away the probability reading for the positive value that is associated with this negative. So what we're going to do here is that we're going to look for 1.25. So again, we go under the Z column and we look for 1.2 and then go straight across on the 0.05. So on the Z column, we scroll down on the Z column until we find 1.2, and then we go across from 1.2 to 0.05, and that's the reading for 1.25. The reading for 1.25 here would be 0.8944. So we're going to take 1 minus 0.8944 here. Yes, and then we're going to simplify this. So this will become 0.7734, which is the probability reading for the positive value in this interval. Take away 1 minus the probability reading associated with the positive number or the absolute value of the negative number. So that probability reading for the positive value associated with this negative number, or we could say its absolute value of 1.25, is 0.8944. Remember that this table does not have negative z values, so that we have to apply the properties of symmetry in order to derive our answer. And so this is why we're going through this particular solution here. In most situations, you are given the positive side of the curve and not the negative side, because it requires more application and more thinking, more critical thinking, to use the positive side of the standard normal table only, which is what we are using in this case. So we're going to take 1 minus 0.8994, 0.8944 rather, and the reading here, 1 minus 0.8944, is, as we found earlier, 0.1056. So 0.1056, there we are. And so this will now give us, I'm sorry, let's just tidy this up a little. So 1 minus 0.8944, all of that actually gives us 0.1056. So we're going to take 0.1056 from 0.1056, and we're going to subtract that value now from the 0.7734. So minus from 0.7734, and that gives us 0.6678, which is the same, if we convert this to a decimal, this would be 66.78%. And this means now that there's a 66.78% chance that the life of a light bulb in this particular population in the problem that we are faced with will fall somewhere in the range of 1850 hours and 2090 hours. There's a 66.78% chance. And so this is how you deal with situations where, after standardizing one of the z values, remember the values under the standard normal curve are called z values, when one of the values is negative and one is positive, again what we did here is that we took the table reading from the standard normal table here. We took the table reading for 0.75, which is the positive value. When you're faced with these situations, always take the reading for the positive value in the interval first, then subtract 1 representing the total probability. subtract, and notice I put this in parentheses for ease of simplification. So you subtract 1 minus the probability reading, meaning the reading from the standard normal table, this table here, of 0.8944 that is associated with 1.25, which is the positive value or the absolute value of this negative result, negative z value that we came up with through standardization. So then we subtracted 0.8944 from 1, which gave us 0.1056, and then we subtract that from 0.7734, which gives us 66.78%. And so what we've looked at here are 3 very common applications of the normal distribution. I will do another follow-up on it, on some other variations that we can get in treating with situations requiring the application of the normal probability distribution to solve problems. Thank you very much.